I'm Dr. Chris Creighton, and in this video we'll be discussing logarithmic functions. The core objectives are determining if a function is logarithmic and converting between exponential and logarithmic statements. So pretty much what we'll be doing is having a logarithmic statement, converting it to exponential, or exponential to logarithmic. And then eventually we'll be able to solve logarithmic equations and determine graphical features of logarithms. So the first basic idea here is that we're going to start off with the fact that f of x is equal to a to the x is 1 to 1, for a is positive and not 1. So in this case here, we have the equation ax is equal to b. And if we wanted to solve this equation, we know that this is an invertible function, so there's some sort of inverse here. And so this would correspond to the point x comma b. So then the inverse will correlate to the point b comma x. And we defined the inverse as g of x is equal to log base a of x. So the logarithm base a is defined to be the inverse of f of x is equal to a to the x. And so this inverted point here, which we just swapped the order, would correspond to log base a of b is equal to x. So the important bit here, this is an exponent of a that gives the value of a to the x equaling b. So this is the exponent of a. So logarithms are exponents that give us certain values. So for example, if we have a logarithm statement like log base 2 of 4 is equal to x, the corresponding exponential statement, by switching the forms, would say 2 to the x is equal to 4. Now going back to the idea of exponential equations, we then will solve this by saying, well, 2 to the x is equal to 2 to the squared, so then x is equal to 2. So what that is telling us is that log base 2 of 4 is equal to 2. So what this is saying is that this is the exponent, 2, that when we square, well, 2, it gives us 4. So what this is saying is that 2 squared is equal to 4. So let's convert some more between exponential and logarithmic forms. So for example, this first one here. This is saying 3 to the negative third power is equal to 1 over 27, which is completely true. So converting to log form, this would be log base 3, the base is that, so that's our base, of 1 over 27 is equal to minus 3. So what this is telling us is that the logarithm itself is the exponent of our base that gives us the value on the right, or the value 1 over 27. Just like here, converting this one to exponential form, which is the most common way to evaluate or figure out values of logarithms, what this is telling us is that the base 4, so we have our base of 4, giving us our value 2, 2 is our exponent, this is equal to the value 16, which is completely true. So 4 squared is equal to 16. So converting this, the logarithm value, so what the logarithm equals, is the exponent. Logarithms are exponents of the base of the logarithm to give us the value of what's on the inside. Next, converting 7 to the 0 power, which is also 1, into log form. This would tell us that log base 7 of 1 is equal to 0. So that's quite nice. Converting this next one into exponential form, what this is telling us is that the base of 1/2 to the minus 3 power is equal to 8, and that is completely true. The negative of the exponent converts that fraction to 2 cubed, and 2 cubed is 8. And then for our last one here, log base 3 of 3 is equal to 1. To see why that is in fact true, we do exponential form. And this is 3 to the first power is equal to 3, which is rather nice to know. So log base 3 of 3 is always going to be 1. Let's solve some logarithmic equations. So the first one here is log base 2 of x is equal to 3. So what this is telling us is that 3 is the exponent of 2 that gives us x. So converting this into exponential form, which is again the number one way of evaluating or solving logarithmic equations, this is telling us that 2 cubed is equal to x. So in this case here, x is 8, which completely makes sense. In this case here, 3 is the power of 2 that gives us 8. So 2 log base x of 8 is equal to 2. So this one we don't know the base. So converting this into exponential form, this tells us that x squared is equal to 8. So whatever x is, it satisfies x squared is equal to 8. So in this case then, x is equal to plus or minus the square root of 8. But importantly, this is a base, so x is greater than 0, which restricts us down to x is equal to the square root of 8, which can be simplified down to 2 root 2, if you would like to. Next, log base 3 of 27 is equal to x. And this is how we evaluate logarithms. We convert them into exponential form. This is asking what power of 3 gives us 27. So in this case here, converting it to exponential form, this tells us 3 to the x is equal to 27. And now we're home in exponential equations. So we should recognize that 27 is equal to 3 cubed, so x is equal to 3. So in this case here, to evaluate logarithms, the way that I like to think about it is I'm like, oh, this is equal to x. Convert it to exponential form and solve the corresponding exponential equation. So let's evaluate some logarithms, continuing on with this idea. So the way that I like to evaluate logarithms is I'm like, okay, I'm going to call the evaluation x, and we need to figure out what that is. So in converting this into exponential form, what this is saying is that 7 to what power is equal to 49? And again, we're back in exponential equation land. So now we can recognize that this is 7 to the x is equal to 7 squared, so x is equal to 2. This allows us to conclude that log base 7 of 49 is equal to 2, which is true. 7 squared is equal to 49. Second, log base 3 of a third. This is what power of 3 gives me 1/3. And in this case here, I'll just do it with x. So some of these you should know and go like, oh, I think this is -1, but this is how we would solve it. So in this case here, we get 3 to the x is equal to 1/3. So then 3 to the x is equal to 3 to the minus 1. So in fact, it is true that x is -1, which then allows us to conclude that log base 3 of a third is equal to -1. -1 is the power of 3, which gives us 1/3. 3. Log base 1/2 of 1. Now this one looks a bit more complicated, but honestly, if you just view these as exponential equations by setting it equal to x, and then converting it, so this is 1/2 to the x is equal to 1. Now this one looks a little tricky, but the thing is that everyone should recognize that 0 as an exponent to anything always will give us 1. So in this case here, it's 1/2 to the x, which is 1/2 to the 0 power. So x is equal to 0. The only exponent for anything that gives us 1 is 0. So in this case here, log base 1/2 of 1 is equal to 0. And that pattern will hold. And then lastly, 4. Log base 2 of 3 root 4. Now this one seems more complicated, but if you remember going back to exponential equations, that's equal to x, which then promptly converts to 2 to the x is equal to the cube root of 4. Well, 4 is 2 squared, and the cube root is a fractional exponent. So then this converts to 2x is equal to 2 to the 2/3. So x is in fact 2/3, yielding the logarithmic value, log base 2 of 3 root 4 is equal to 2/3. That's completely fine and completely valid. That can happen. So the properties of logarithms. So in this case here, we're always going to assume that the base a is positive and not 1. So the first one is log base a of a is equal to 1. And the reason why that's true is that this is equivalent to the exponential equation a to the 1 is equal to a, which is completely true. Second, log base a of 1 is equal to 0. And that is because if we have the exponential equation, this is a to the 0, which is always equal to 1, no matter what a is. Well, as long as a is positive and not 1 in this case. Now, what about the next two? Log base a of a to the r. Well, this is considering the fact that these are inverse functions. So if we plug one into the other one, you're going to get the value you initially plugged in. So that's one way of viewing it. Alternatively, log base a of a to the r as an exponential equation is just a to the r is equal to a to the r. It's kind of like redundant there, but the basic idea is simple. What power of a gives us a to the r? And the answer is r. Likewise, a to the log base a of r, log base a of r is the exponent of a that gives us r. So in this case here, it's just r. Log base a of r is that exponent that gives us the value r, no matter what r is, as long as it is positive.